Hello everyone. RecurDyn is widely recognized for its multi-body dynamic analysis. In addition, RecurDyn offers static analysis capabilities to accurately determine the equilibrium state of complex multi-body dynamic systems. Today, I will cover the static analysis capabilities available in RecurDyn. This webinar will proceed in the following order. First, we will find out how static analysis can be used in RecurDyn. Next, we will discuss how RecurDyn's system-level static analysis differs from conventional static analysis. Then, I will explain the unique advantage of system-level static analysis with F-flag static. Finally, I will introduce remarkable system-level static solutions performed using F-flag static. Then, this is the first topic. Is static analysis possible using RecurDyn? The answer is yes. RecurDyn enables you to easily perform static analysis. You can generate the meshes, apply boundary conditions, and perform static analysis, then you can immediately view the results. Let's see the video here. Create a multi-body model. Then generate the mesh. Define boundary conditions and apply external forces. Run a static analysis. After that, perform post-processing. Then, how RecurDyn's system-level static analysis differs from conventional static analysis. To understand the system-level static analysis, it is essential to know the difference between FEM static analysis and static analysis with RecurDyn multi-body dynamic software. FEM was developed to observe the stress in a structure under load conditions. On the other hand, static analysis in multi-body dynamics primarily aims to find the static equilibrium state before performing dynamic analysis. Both methods deal with the same equations of motion, but their objectives differ, leading to variations in the approach. Since FEM deals with large degrees of freedom, equations were solved for small deformations and force equilibrium conditions to reduce computational speed. The quasi-static analysis method is used to implement geometric nonlinearity and material nonlinearity. In this process, specific and clear boundary conditions are essential. However, in multi-body dynamics, calculations are performed to find the static equilibrium of a system. Boundary conditions in multi-body dynamics are often less defined, for example, contact conditions. Furthermore, dynamic systems frequently involve large displacements and significant deformations. The ability to handle all these conditions without numerical divergence is critical. The model on the right shows the extreme difference between the two solutions. This model consists of a cantilever beam and a pendulum. This looks simple, but this is a challenging problem for static solvers. Dynamic analysis engineers would think that this problem can be easily solved with a static solver. However, the pendulum model cannot be solved statically with FEM solver. To solve this problem, you have to input a very small rotational stiffness into the revolute joint. On the other hand, multi-body dynamic software easily solves the static equilibrium of this model. While it may seem similar to conventional static analysis method, there is a huge difference here. Let's briefly go over static analysis. In general, static analysis involves calculating the stiffness matrix of a finite element model, and then applying boundary conditions to compute the external force vector, F. Then, we calculate the inverse matrix of the stiffness matrix and multiply it by the external force matrix F to calculate the small deformation, delta Q. This calculation is only possible if the stiffness matrix can be inverted. Therefore, this equation cannot be solved if it has rigid body modes. Furthermore, large deformation and large displacements cannot be calculated. In traditional static analysis, to overcome these limitations, quasi-static analysis is used. This method calculates the static equilibrium state of the final condition by incrementally changing the load or displacement. During this process, the stiffness matrix is updated at each step, allowing geometric nonlinearity to be considered. Now, let's take a look at static analysis in multibody dynamics. Static analysis in multibody dynamics involves formulating the equations of motion for the joints and external forces and calculating equilibrium by incrementing delta Q through NR iteration. This calculation automatically updates the stiffness matrix of each step and calculates considering geometric nonlinearity. Of course, changes in the external force vector corresponding to delta Q are also considered. As a result, the system efficiently and stably converges to its static equilibrium state. So, what exactly is the RecurDyn's F-flex static? It is a feature that enables static analysis for even highly complex systems that include flexible bodies, so-called F-flex bodies. Mathematically, it seems that you just need to include the stiffness matrix of the flexible body in the stiffness matrix. However, it is not that simple. If it were that simple, this calculation would have been possible with other solvers. To make this functionality possible, FunctionBay developed a static analysis solver specifically for MFBD equations of motion. We also enhanced the accuracy of Jacobian calculations for contact equations and implemented numerous technologies to improve computational efficiency. This groundbreaking feature took several years to complete. Now, static analysis is possible for highly complex mechanical systems that include rigid bodies, R-flex bodies, and F-flex bodies. So, what can you achieve with F-flex static? The first application is general structural strength analysis through the static analysis. Here, you can see the vehicle door, lower control arm, and the knuckle. As you can see, the static analysis results can be obtained within just a few seconds. In this model, it took 58 seconds, but for low control arm, it took just 2.6 seconds, and for knuckle, 0.8 seconds. Additionally, you can see the time, step, and CPU time. Time here refers to the time used in the external force expressions, not simulation time. Step is usually set to 1 for general static analysis. However, for quasi-static analysis, a value greater than 1 is used. CPU time indicates the calculation time. Pay attention to these values. You will see how fast RecurDyn's static solver is. Next, I will show you transient static analysis. This involves applying various system conditions as a function of time using joints and motions, and then performing static analysis for each time step. As shown in the video, this allows static analysis of multiple states for a single model. This is one of the most significant features of RecurDyn's static analysis. With traditional FA static solutions, you would need to rebuild the model for each condition. The results of 3 transient steps can be obtained from the excavator model. From this one, however, the animation includes intermediate states during the convergence process, which is why a large number of steps are displayed here. The number of steps used for this static analysis is just 3. The same applies to the delta robot animation. Although static results for 10 steps are calculated, the animation includes intermediate results during the convergence process. This is the large deformation analysis. The model on the left is a break oil line. It analyzes 4 steps, and as you can see, a large deformation occurs. But the results can be viewed quickly through static analysis. The model on the right shows the wrinkle over film. Here, This model is particularly challenging for static analysis to converge due to simultaneous translational and rotational displacements of the shell body. Nevertheless, as shown, it converges very effectively with RecurDyn static solver. It took only 116 seconds. Finally, static equilibrium of a complex system can be obtained using F-flex static. Most dynamic analysis engineers will likely use this type of analysis the most. All mechanical systems on Earth start operating in a state of static equilibrium in a gravitational field. A typical example of this is a vehicle. A similar example would be the landing gear of an aircraft. In the case of the landing gear on the left, it starts while suspended in the air, but it begins operating after achieving an equilibrium state on the ground. The same goes for the vehicle. On the right, you can see how well it converges in the vehicle model. You can see that both the landing gear and the vehicle models converge very well. Both models include several F-flexible bodies and can be calculated using F-flex static. Once again, the animation you are watching depicts motion, but it does not represent the actual movement. Instead, this animation includes the process of finding the static equilibrium state. Each frame of the animation corresponds to an intermediate stage of the computation. However, as you can see, only one step is used for each simulation. Here and here, step 1, and the actual result corresponds to the final frame of the animation. Now, let's explore the unique advantage of system-level static analysis with F-flex static. First of all, the most important advantage is the calculation speed. When running dynamic analysis, certain models can take a long time. However, by utilizing static analysis, the process can be significantly faster. The model you see here is an example model of a pin insertion into a track link. While it takes approximately 6 minutes to analyze it using dynamic analysis, static analysis completes the same process in just 2.8 seconds. This is an incredible reduction in computation time. Static analysis also provides advantages in defining the context stiffness. In dynamic models, applying large stiffness values can be challenging because they can reduce the step size, resulting in long computational time. However, in static analysis, inputting a large stiffness value does not significantly affect convergence. This can sometimes result in more accurate outcomes. Static analysis enables rapid simulation of models with large deformation. The model you see here is CTBA, coupled torsion bar axle. In this model, the deformation itself generates torsional stiffness, resulting in significant amounts of deformation. If dynamic analysis were used, it would require considerable computational time. However, with static analysis, the simulation can be completed quickly, even for various scenarios. Additionally, special force elements such as a tire can be directly applied without any issues for this kind of static analysis. This is truly an efficient analysis capability. This is similar to what I mentioned earlier. You can perform static analysis for various conditions with a single model. This means there is no need to rebuild the model for each posture that changes over time during static analysis. The model you see here is a robotic arm that includes contact and on-off joints. It is used to analyze the stress of the arm under different conditions. The model shown here is a stacker. A stacker is a system designed for transporting and storing items. This is not just a result of dynamic analysis. Instead, multiple static analyses for the desired states were performed sequentially, using motion and contact. While it took 53 minutes to achieve convergence, performing the same analysis with dynamic analysis would have taken significantly longer. This highlights a key advantage of F-flex static. So far, I have explained the unique advantages of system-level static analysis. Now, let me introduce several examples that demonstrate the remarkable effectiveness of performing system-level static analysis using F-flex static. The first model is a CV joint boot. This model represents a typical example of nonlinear FEM software. In this CV boot model, it exhibits large deformations, complex contacts, and buckling. However, the RecurDyn static analysis achieves convergence efficiently and completes the analysis in just 1 minute 49 seconds. In other words, RecurDyn static analysis demonstrates significantly faster computation speed compared to performing dynamic analysis. This example demonstrates performing static analysis under lateral acceleration conditions on the vehicle model, which represents the full vehicle model. Its chassis and lower control arm are modeled as flexible bodies. As you might expect, performing dynamic analysis on models that include large flexible bodies can take a significantly long time. So, system-level static analysis was used for this model. In this case, the static analysis was completed in just 5 minutes and 30 seconds. This model also includes the effects of specialized force elements such as tires. And despite the presence of such complex elements, the static analysis was performed seamlessly. All the models shown so far can be used for both dynamic analysis and static analysis. This capability, which is challenging for other software, effectively eliminates the boundary between dynamic analysis and static analysis when using RecurDyn. While dynamic analysis is essential when the dynamic effects such as inertia or vibration play a critical role, static analysis becomes a powerful tool in scenarios where these effects are minimal or can be reasonably neglected. In such cases, static analysis allows engineers to quickly refine models and set approximate directions, making it a valuable tool for early-stage decision-making. This example is the pantograph of a railway vehicle. In this model, the catenary wire and the overhead wire are essential components. The catenary wire is positioned at the top, while the overhead wire is located below. These two wires are connected by a dropper, which ensure that the overhead wire remains straight. The pantograph remains in contact with the overhead wire while the tray moves. To analyze this system, it is necessary to model the overhead wire and the catenary wire and establish a static equilibrium state. In this model, both the overhead wire and the catenary wire are modeled as finite element beams. Droppers are not simply attached. They are connected to both the catenary wire and the overhead wire via contact. Additionally, both ends of the wires are connected to tension control devices to apply the required tension. This page shows the results of the static analysis on the overhead wire. The solution converged successfully, although it took approximately 8 minutes to achieve equilibrium. Performing a dynamic analysis would require significantly more computational time. This static analysis model is indeed highly complex and challenging. It requires exceptional convergence performance. The video below illustrates the final dynamic analysis conducted with the pantograph model. The next example demonstrates an analysis of raising a flag. While this model can also be analyzed using dynamic analysis, static analysis was conducted to verify its convergence. Even though this flexible body is very thin and inherently unstable, the RecurDyn's static solver achieved accurate convergence. You can see the flag being raised here. This is the final example. The tape spring model demonstrates the most remarkable results among all the examples presented so far. This device is a component used to deploy the solar panels of a satellite in space. Although it is an extremely lightweight structure, it provides sufficient stiffness once fully deployed. the device is transported in a folded state on the satellite. Thus, the transition process from the folded state to the fully deployed state is critical. To conduct the analysis, the model must first be created in its folded state. For this model, performing dynamic analysis for the folding process required approximately 3 hours. If the default context stiffness is set to high, the simulation time could exceed 10 hours. However, for this model, obtaining the initial folded state does not necessarily require dynamic analysis. Therefore, the static analysis was used instead. The computation time was only 36 seconds, which is exceptionally fast. Even though sufficiently high stiffness was applied, the simulation time remained remarkably short. Anyone familiar with similar simulations using FE software would understand how impressive this performance is. The video on the right demonstrates the dynamic analysis of the folded tape spring being deployed from the initial folded state. Calculating the initial state using a static solver and then performing dynamic analysis based on that initial state is one of the most common use cases of F-flex static. So far, we have explored F-flex static and its unique advantages for system-level static analysis, along with several examples. RecurDyn offers a solution beyond conventional methods by enabling high-performance static analysis in dynamic models. Various static analyses for diverse scenarios can be easily implemented within a single model. Transitioning to dynamic analysis is simplified by achieving static equilibrium state as an initial condition. Moreover, even nonlinear deformations caused by contact can be solved quickly and accurately with RecurDyn. With these capabilities, RecurDyn's system-level static analysis opens numerous possibilities. We hope it will be widely used in the field, providing greater support for CA tasks. Lastly, before concluding my presentation, I'd like to share an interesting example with you. Can you guess what this is? It is a special bow that was used in Korea a long time ago. This is the typical shape of the bow when carried by an archer. However, in battle, the bow is bent and strung with a string. I modeled this special bow using RecurDyn and conducted a simulation. The basic shape of this bow is shown on the left. However, when it is bent and the bowstring is attached, it becomes the shape on the right. Let's take a look at this video. From this video, you can see how powerful this traditional Korean bow is. Its unique shape allows it to push the arrow all the way through, maximizing the conversion of elastic energy into kinetic energy. Without the F-flex static analysis feature, simulating such a model would have been extremely challenging. However, with RecurDyn's system-level static analysis capability, creating and simulating this type of model becomes remarkably easy. This concludes my presentation. If you have any questions about RecurDyn's remarkable static solver, please feel free to contact us through our website. Thank you.